Hello and welcome to the final episode of the year of Lexx Education, the comedy science podcast where comedian me, Laura Lexx, tries to learn science from her non-comedian younger brother Ron.
That's me, Ron.
It's Ron! Hope you've had a lovely Gooch week, everybody. Did you have a good Christmas? That's when everybody tells us how they got on for Christmas in that little clip I left there, Ron. It's not Christmas hasn't happened for us yet, has it, Ron? It's currently the 18th of December when we're recording this, but we don't want to.
We're 1 week out.
Week. Yeah, we are. I'm done with my interest in Christmas by Christmas Day, so it's over a week from today in my head. But everybody else is having the time of their lives. But we're recording this a teensy bit early just so that we can have a chill week base, innit, Ron?
Innit.
Also, you haven't edited this episode yet, so if we do the intros, outros now, I can just stick them in the shared folder and you have to put them on, tack them on, and I'm done with editing for 2024.
Yeah, maybe I'll do that this afternoon.
Yeah, because I've put everything online, Ron. I'm good to go. Edited Boy in C3 last night.
The one everyone's been waiting for.
I think they have, mate. That's coming out in a couple of days. 3rd of January that lands. So if you're a patron, you're getting that. If you're not, then, I don't know, become a patron probably. Make that your New Year's resolution. Ron, have you got any New Year's resolutions?
It's not New Year's yet.
No, but it is when they're listening to this.
I think 2025 I'm really going to focus on my macros.
Yeah, okay.
What about you?
Micros, probably. I'm going to
I think you're getting quite enough micros.
The small of stuff. No, do you know my plan for 2024-25, Ron? I'm just going to kill it. I've got a big year planned. Like, I've got a holiday in January. We've got Leicester Festival in February. I'm going to New Zealand in May. I've got Edinburgh Festival in August. I've got Aberdeen. Oh, and I've got a tour of Scotland in April. Then Aberdeen in September. Then kicking off, putting a tour on sale to go on tour spring 2026. So plus writing Pivot 2. So I'm just going to be like bouncing from project to project, launching a new online project too. We start filming that in January. I'm just full of projects and looking forward to A-level too.
I'm looking forward to A-level.
It feels like so long since we were just doing normal episodes. It's quite exciting.
Do you know what I'm not looking forward to with A-level?
Me?
Separate quiz records.
Well, maybe we'll mess with the format. We can change it if it makes you sad, Ron.
It's just a lot. We've talked so much about our crazy timeline with recording. Sorry, work email. Oh my god.
Why can't they just leave you alone?
Maybe we will, because it's crazy to keep on top of it.
It's not that hard, Ron.
Here's what I think you should do for your New Year's resolution.
We'd sit down, here's the thing, Ron. Every time we'd sit down, we'd still have to record an intro, an episode, and a quiz. It would still be the same amount of stuff being recorded. It's just at the moment, it's a quiz to a different episode.
Yeah, and then it's like, when's this one going out? What's this the quiz for? Who?
But that chaos is part of it, man.
Yeah.
It's who we are. It's what we do.
That's right.
Anyway, speaking of chaos.
Here's what I think you should do for your New Year's resolution, though. You know how you have a personal trainer?
Yeah.
What if you just stopped working out one half of your body and just focused on the left?
I don't want to do that. I think I'm already a weird enough looking person as it is. I don't think we need to have like a shriveled half, like two-face but two body. I don't think anybody needs that.
One plump, one ripped.
I'm not even sure that the plumpness would stay on that half. It would just be like atrophy and normal. Because like I've been working out for 8 years and I'm not ripped. Women don't really get ripped unless they're on an awful lot of extra protein.
But if like that's with you spreading all of your current effort across both sides, whereas like feasibly you're going to be doubling the output on the left-hand side that you are working at. And
Why
especially
don't
like
you do the other side? You do your right side, and then at live shows,
we can lock elbows and just fight everyone.
well, look, Jen is coming in an hour and 15 minutes, so I will
Pitch it to her.
I'll pitch it. Okay. Speaking of the chaos that we were speaking out before that chaos, the episode you're about to hear is the second half of the chemistry exam that we started right back at the beginning of December before we did Christmas trees and the Grinch. So you may need to go back and re-listen to that first chemistry exam. But this is the second half, so enjoy.
Gnocchi's in between my microphone and the pop stand.
That cat is a menace. I do like her, though.
She is good. Hello. Hello. Yes. Hello. All right, Laura. Question 4. Laura?
Mm-hmm.
Question 4.
Yes.
This question is about electrolysis. A student investigated the electrolysis of copper chromate solution. Copper chromate solution is green. Copper chromate solution contains blue-coloured copper 2 plus ions, yellow-coloured Cr chromate ions, 2 minus. Figure 1 shows the apparatus used.
Oh, there's a really cool YouTube, and I don't mean the one you watch and get told you're a silly fat slut on. I mean a tube that's the shape of a U, that's got green copper chromate solution in it. Oh, wrong. Can me and Charlotte the podcast come and stay with you on the 22nd of November, please?
I don't think I'll be here.
Why?
I'll be in Brussels. Am I
I'll
back
tell her
by
you
then?
don't love
I don't think
Okay.
I'm back by then.
And then they've got a DC power supply with plus tube going in one side and a negatron tube coming in the other side.
I can leave my keys with Max and Amelia, though, if you want to stay here.
No. Don't worry about us.
Why are you being like this?
Because I don't want to do this exam, so it's easier to pick a fight with you and then we don't have to answer questions.
Let's not do that. The student switched on the power supply. The student observed the changes at each electrode. Table 4 shows the student's observations. Changes at the positive electrode, the solution turned yellow and bubbles formed. Changes at the negative electrode, the solution turned blue and a solid formed on the electrode. Laura, explain why the colour changed at the positive electrode.
Because the positive electrode attracted the... what were they called? Chromacon 2 minus ions. I'll just write Cr042 minus ions to it.
Chromate.
They
Yep.
gathered at that electron due to their negative charge being attracted to the positive charge of the electrode.
Okay. The gas produced at the positive electrode was oxygen. The oxygen was produced from hydroxide ions. Name the substance in the solution that provided the hydroxide ions.
Oxygen in the chromate. Chromate. What did you call all those again?
Chromate.
Chromate. Oxygen in the chromate.
The oxygen in the chromate produced hydroxide ions.
Oh, no.
The oxygen was produced from hydroxide ions. Name the substance in the solution that provides the hydroxide ions.
Water.
Is that what you want me to write down?
Is there water? A solution is water, isn't there? That means in water.
Usually, yeah.
Yeah, water, please, Ron.
Describe how the solid forms at the negative electrode.
So the positive copper ions are attracted to the negative electrode. And then when they get there, they form magnetic bonds with each other and solidify into copper pieces.
Final answer?
Yeah, I don't feel good about it, but it's the best I've got.
Bloody hell. Yeah, 4.4. The student repeated the investigation using potassium iodide solution instead of copper chromate. Name the product at each electrode when the potassium iodide solution is electrolyzed.
Negative electrode will have iodine, and the positive electrode will have potassium. Other way around. Negative electrode will have potassium, positive electrode will have iodine.
Final answer?
Yeah, but you didn't do the relief nod that you sometimes do when I've got it right.
Well. No comment. Question 5, Laura. This question is about the development of scientific theories, which I think you're better at because it's history, not science.
Yeah.
Figure 2 shows a timeline of some important steps in the development of the model of the atom. 5.1. The plum pudding model did not have a nucleus. Describe 3 other differences between the nuclear model of the atom and the plum pudding model.
Okay, so the plum pudding model does not have any space in the atom. Whereas in the atom nuclear model, there is space between the electrons and the nucleus.
Cool.
There were no protons in the plum pudding model. The positive charge was thought to be the substance of the atom itself. Whereas in the nuclear model, the positive charge is the protons, and they exist in the nucleus.
Okay.
And a third one, I guess, like, in the nuclear model of the atom, we understand the electrons to be in shells or orbits around the nucleus in a specific structure, which was not recognised within the plum pudding model.
All right. That seems good.
I think, yeah.
Happy with that?
Yeah, I think so. Don't really know how to phrase it for the shells one, because it's like, I don't know, maybe they did think that they were in specific patterns, but I've never heard that said.
Niels Bohr adapted the nuclear model. Describe the change that Bohr made to the nuclear model.
He put the protons outside of the nucleus. There you go.
2 marks for that?
Instead of inside the nucleus where they are on the nuclear model.
Are protons outside the nucleus?
No, they're inside the nucleus.
Yeah, Niels Bohr adapted the nuclear model.
Oh, I thought that meant he changed it.
Yeah. Sort of, but, you know, took the very
Alright, let's say he put them in there then. He was the guy that worked out that they were in the nucleus.
Alright, we're moving on because we're going further away. Mendeleev published his periodic table in 1869. Kenneth Branagh plays Niels Bohr.
I remembered that, Ron.
Yeah.
He did a lot of atom splitting. I knew that.
Mendeleev arranged the elements in order of atomic weight. Mendeleev then reversed the order of some pairs of elements. A student suggested Mendeleev's reason for reversing the order was to arrange the elements in order of atomic number rather than atomic weight. Explain why the student's suggestion cannot be correct.
Use figure 2.
Figure 2 is the timeline at the beginning of the question.
1869. Oh, because he couldn't have known. Mendeleev published his periodic table before the discovery of protons and neutrons, both of which are needed to calculate atomic number.
You're so close. You're so close, and it's come all from your rock-hard brain. Why? But adapt it, Laura. What do you need to work out the atomic number?
The weight of the atom.
No.
The number of protons.
Yes.
Yeah, so that's why I said you need to know the...
No, but you said you need to know the protons and neutrons.
Don't you need to know both?
No.
Okay, just protons.
Yeah, just protons. Woo! You did it!
Yay!
Smashing. Give the correct reason why Mendeleev reversed the order of some pairs of elements.
Reactivity? He put... I don't know. I don't remember that. So what could it logically have been? It must be something like... He already had them in atomic weight. Why would he just change some of them? No idea. Oh, I don't know. Why would you just change some of them in pairs?
What do you know about the periodic table?
It's reactivity, isn't it?
What do you mean by reactivity?
Well, they're ordered in how reactive they are.
What are ordered in how reactive they are?
Elements.
Yep, but elements within?
Groups.
Yep. And they do get more reactive, but what else is there about groups?
Well, they're like metals or gases or stuff at room temperature.
Yep, they're all a state at room temperature. But potassium and lithium are in a group together.
They have the same number of
Beryllium.
electrons in their outer shells.
Yep, but Mendeleev didn't know about that.
No.
Beryllium and potassium aren't in a group. Even if you knew nothing of those structures, you might put lithium, potassium, cesium.
Because they have the same reaction.
Yeah. Did you hear that?
Yeah.
That was my tummy.
Yeah. I know.
Yeah. Yeah. Pull that thread.
So is it order of strength of reactivity?
No. But it's about the reactions that they have.
They had the same reactions to a catalyst.
Same reactions to some catalysts, but also they're all soft in group one, aren't they? They're very soft metals.
Yeah? So they had similar properties.
Similar properties, yeah, to match the rest of
Their group.
Yeah, there we go. You understand that?
Yeah. I just
You
didn't
saw
know that
that-
they weren't already like that, though.
No, he didn't get them in the correct order automatically. But then part of the genius of it is he didn't just look at those numbers and go, "Oh, that's weird that these ones don't line up." He went, actually, if I swap these round, that actually makes more sense because then the properties are all the same. So there must be, he sort of worked out that there must be something about these that they all have in common to be reacting the same. We then found out, like in the example of group 1, they've all got one electron in their outer shell. So they all react the same to the same stimuli. But he worked that out kind of before knowing any of the structural stuff, which is why the periodic table was cool.
Yeah.
I'm just going to put correct.
Mendeleev.
Mendeleev. Question 6,
Put your
Laura.
little itty-bitty metals in the row. Mendeleev. Mendeleev. Are they reacting the same? Yes or no?
This question is about displacement reactions. 6.1. The displacement reaction between aluminium and iron oxide has a high activation energy. What is meant by activation energy?
It's the amount of energy required to start the reaction between the... Just to start the reaction.
All right. 6.2. A mixture contains 1 kilogram of aluminium and 3 kilograms of iron oxide. The reaction for the equation is 2 aluminiums plus 1 iron oxide equals 2 iron and 1 aluminium oxide. Show that aluminium is the limiting reactant. Then it gives the relative atomic masses of oxygen, aluminium, and iron. Blood loss setting in.
Yeah. I lost loads of blood today. Right. So I've got 2 ALs. 27 is an AL. So 54 plus... Why do some of them have a small number and some of them have a big one again?
No.
What?
Too basic. You should know that.
Is that... I don't know if that does a different thing to the sum. Okay, well, let's just pretend it doesn't. So, 54 plus 112 plus 48. Is this helpful? What am I trying to do? Oh, God. That's not helpful. The mixture contains 1 kilogram of aluminium, 3 kilograms of iron oxide. The equation for the reaction is that show that aluminium is the limiting reaction. So I've got to show that we run out of aluminium, haven't I? Okay, so 54 aluminiums. Does that help? 1,000?
Well, no, 54 is the weight of aluminium that you have to input every time.
Yeah?
Yeah. Yeah. Yeah.
Yeah.
Yeah.
And then you get 54 out, don't you?
It doesn't really matter what you get out.
So...
Because we're talking about reactants.
It's 54 plus 160 equals...
Why are you adding the 160?
I don't know, Ron.
It's more about, if you think about it, I think you'd have got there on your own. But do you not think it's probably more about the relationship between 1 kilogram of aluminium and the weight of aluminium and 3 kilograms of iron oxide and the weight of iron oxide than it is about adding those two numbers together. Because if you add them together, then they're one number. And then how can you talk about aluminium?
I don't know. I've got no idea. So what about 1,000 divided by 54? That gives me 18.5 experiments that I can do with my aluminium. And then 3,000 divided by 160 equals 18.75 experiments I could do with my iron oxide. So using that maths, you can see I can do fewer experiments with the aluminium.
Well done.
I'm doing
Dash
really well.
help. 6.3.
How many questions are there?
We're on page 17 and it goes to page 29.
Okay.
Magnesium displaces zinc from zinc
No,
sulfate.
not zinc manganese. Oh
Complete.
no.
The ionic equation for the reaction, you should include state symbols. Stop thinking of a joke about state symbols and start thinking about the equation.
Sorry. That was Missouri. Tom. Ron. I just called you Tom. That's creepy.
Yeah.
Right. Oh, God. So magnesium as a solid plus zinc 2 as an aquatic leads to zinc sulfate. What the hell is sulfate? Magnesium. So I guess we're going to get magnesium sulfate.
If they've not given you the sulfate, you could probably ignore it.
Yeah. So, well, I guess then the magnesium's going to become AQ plus the zinc will become a solid, maybe? I don't know. Is the 2 plus, do you reckon that goes to the magnesium? Yeah. Let's say Mg2 plus aqua plus ZnS.
Final answer?
Yeah.
Alright. Explain why the reaction between magnesium atoms and zinc ions is both oxidation and reduction.
Because the magnesium oxidizes in solution.
What does that mean?
I don't know, Ron.
Right,
Well, I've got to say it's oxidation. All right, the magnesium bonds with oxygen in the solution.
Where's the oxygen? Where's the oxygen?
In the solution!
But you've just done the equation.
Well,
and
I don't know if
oxygen-
it's right, though. Okay, it's right. Great.
But there's no oxygen in the inputs.
So how can it be oxidation?
Because that's not what oxidation means.
I don't know what oxidation means.
I'm just going to write that. I don't know what oxidation means. And we can move on.
Ooh, you're mean.
This is my evening as well that you're wasting.
I'm not wasting it. You've wasted 2 years of my life teaching me nothing.
7.1. A student drew a the reaction between hydrogen and oxygen releases energy. A student drew a reaction profile for the reaction between hydrogen and oxygen. Figure 3 shows the reaction profile. The student made
So
2
we've got a
errors.
surprised face, but side on. Ah?
I don't see the surprise, but it does look like a
No,
nose.
because it's a reaction profile.
Right.
I wasn't talking about the graph, Ron.
Oh, no, but turn your head. It does look like a nose.
Yeah, it does look like a nose, doesn't it?
Anyway, the student made 2 errors when drawing the reaction profile. Describe the 2 errors.
Taking science and continuing with science. How about that? Ron nearly laughed at that, just for the listener. I want you to know. Oh, God. So, the overall energy change ought to go from the first horizontal line of the table right up to the peak of the line. And the activation energy is wrong too. The activation energy ought to be at the point where the line starts to go up, because that's where the reaction starts.
Activation energy ought to be where the line starts to go up, as that's where the activation starts.
Wait, that's not right.
Read the question again. Perhaps out loud for the listener.
A student drew a reaction profile for the reaction between hydrogen
The
and
whole
oxygen.
question?
The reaction between hydrogen and oxygen release. Yeah, sorry. I think the activation energy arrow, should point to the bit where the line starts to go up. That's what I think.
Okay. 7.2. The reaction between hydrogen and oxygen in a hydrogen fuel cell is used to produce electricity. Hydrogen fuel cells and rechargeable cells are used to power some cars. Give 2 advantages of using hydrogen fuel cells instead of rechargeable cells to power cars. You look so worried.
Byproducts from hydrogen fuel cell is just water rather than CO2, which is bad for the environment. Rechargeable cells require lithium, which has catastrophic mining implications.
Say mining implications.
Yeah, it's really bad where they mine lithium.
Yeah. Alrighty, Roo, 7.3. Reactions occur at the positive electrode and at the negative electrode in a hydrogen fuel cell. Write a half equation for one of these reactions.
H plus arrow negative electron. No idea.
7.4.
Oh, God.
Yeah, Laura,
Yeah,
we have to do physics after this.
I don't want to.
The 3 states of matter can be represented by a simple particle model. Figure 4 shows a simple particle model for hydrogen gas. Give 2 limitations of the simple particle model.
I have no idea.
How does hydrogen exist as a gas? You have to move on.
Pairs? Pairs? Is it pairs?
Do you want to move on?
Is it pairs, Ron?
It might be pairs.
Okay. It's not pairs. The simple particle model is not pairs.
Simple Apples, not pears. Do you want to say anything else, or should we move on? Right, let's move on. Question 5, 7.5. The hydrogen gas needed to power a car for 400 kilometres would occupy a large volume. Suggest one way that volume could be reduced.
Have hydrogen in a solid form. Or liquid, probably. Never heard of solid hydrogen. Have hydrogen in a liquid. Liquid hydrogen.
Final answer?
Yeah.
7.6. The energy needed for a car powered by hydrogen fuel cell to travel 100 kilometres is 58 megajoules. It's a really big shop that Mum loves. The energy released when 1 mole of hydrogen gas reacts with oxygen is 290 kilojoules. The volume of 1 mole of gas at room temperature is 24 decimeters cubed. Calculate the volume of hydrogen gas at room temperature and pressure needed for the car to travel 100 kilometres. Is that just a flat no, or... This one's pretty simple. I believe you to be able to do this one. You can do this one. This one's not even about science. This is just simple maths. You don't even need to change the units for the volume. They want it in decimeters cubed. Now work it out. Do it. Come on, what's step one?
Oh, stop talking when I'm trying to think!
It's a podcast, Laura.
So just edit out 1 or 2 silences per episode.
Fine, alright.
Your head looks tiny. You've got well beefy forearms. I'm just going to take a screenshot to send to Judith. You look like a cartoon of a sailor. The energy needed for a car powered by a hydrogen fuel cell. 100 kilometres.
"29 minutes.
Oh, for fuck. I don't even know where to start. What's a megajoule? Oh, we'll come back to this. This is making my brain hurt.
Okay, we're skipping this one. Okay, I'll highlight it in orange so that we know that one you wanted to come back to. Alright, 8.1, Laura. This question says about halogens. Table 5 shows the melting point and boiling point of some halogens. We've got fluorine, chlorine, and bromine. Their melting points and boiling points. What is the state of bromine at 0 degrees Celsius and at 100 degrees Celsius?
So
We've got gas, liquid, liquid, gas, liquid, liquid, solid, gas, solid, liquid.
So it melts at -7, so at 0 it would be liquid. And it boils at 59, so I think it would be liquid gas, Ron.
Smashing. 8.2. Explain the trend in boiling points over the halogens shown in table 5.
The boiling points of the halogens get higher with fluorines lowest at -188 degrees C and bromines the highest at 59 degrees C. The trend. Is there a trend? 150 different cells, 90 different. there is a bigger gap between the boiling points of fluorine and chlorine than between chlorine and bromine.
Not to shut you down, because everything that you're saying is correct, but this is an explain question, not a describe question.
Okay, so why would the boiling point get lower, higher? Because the bonds are stronger. The boiling point of bromine is higher than fluorine because it has more electrons, and because metals pool their electrons in a metallic bond, so the more electrons...
It's not a metal.
Oh, Christ, on a bike. Ah!
Why does it have more electrons?
Because it's lower down the table.
Did you hear that?
Yeah.
That was my tummy.
I know. Okay, so it has a higher boiling point because it has stronger bonds
Between
its atoms. And when
how do halogens exist when they're just an element?
gas, I think.
But if we're talking about how they
I don't know.
exist,
I don't know.
it's always the same answer, Laura.
Pairs? Is it pairs?
Pairs! Yes, and what are those pairs?
Bromines? Bromides?
What type of thing are those pairs?
Covalent bond. Ionic bond.
Wait, no, go back to the first one.
Covalent bond.
And that, what does that make them?
Bonded. Molecules.
Molecules. So to melt something,
You
or
break
boil
the molecules apart.
the molecules have to go apart, but you're not breaking the bonds between the atoms, are you?
No.
Because it stays in that molecule.
Does it? Yeah.
When you boil water, does it turn into hydrogen and oxygens, or does it stay
'cause
water?
Bubbles come out,
Do you think those bubbles are oxygen?
aren't they? What are the
Fuck me. Really?
What are the bubbles?
Water as a gas. Did you think that was oxygen fleeing the water?
Yeah.
Right, we're moving on. If you thought that, you're not getting this. Why is it not correct to say that the boiling point of a single bromine molecule is 59 degrees?
Because you can't boil a molecule.
Why can't you boil a molecule?
Because atoms are always never alone. Why can't you boil a molecule? Because you just can't. It's too small. Because all that is doing, if you just boiled a single molecule, it would just judder and move about more.
Because boiling is to do with that molecule's
Bonds breaking.
between
Molecules. Atoms.
which one?
Atoms. Molecules. Molecules.
We just talked this through.
Molecules.
We just talked it through seconds ago and I'm cross now.
Molecules, Ron. Because you're breaking apart a molecule off another molecule. So if you boiled a single molecule, it's already stateless because it's a single molecule.
Yeah.
It's the connection between the molecules that defines the state.
Yeah.
I'm going to listen so hard in A-level so that we never have to go through this again.
This is rough.
It's
this
horrible.
is really horrible.
I'm really sad.
Yeah, you're not doing well. Iron reacts with each of the halogens in their
that's
gaseous...
boosting me up for the last 5 pages. Thanks, Ron.
Figure 5 shows the apparatus used. Halogen gas in, heat, iron, glass tube, excess halogen gas out. Give one reason why this experiment should be done in a fume cupboard.
halogen gas is dangerous to breathe.
Yep.
Is that true?
That's what you've said. I've written it down. Explain why the reactivity of halogens decreases going up the group.
That says down the group.
Down the group.
Mistrial.
All right, we'll start again.
No, I just get acquitted of science.
You just want to stop.
It would be funny, wouldn't it, if this was just how the podcast ended? We just got partway through an exam and went, don't want to, bye.
Only 20 minutes left to go, Laura.
If we did stop doing the podcast, how would you leave the Discord before we stopped doing it?
I don't think I'd bother to leave.
I wouldn't be able to see their little broken lab rat hearts.
I've got notifications turned off.
Oh, I haven't. I quite enjoy it. The halogens. That's helium, neon, argon. Explain why the reactivity of the halogens decreases going down the group. Oh, fuck. It's to do with... It's like... Oh, what is it? It's because on the other side, they get more reactive as you go down because the electron is further away. The outer shell is further away from the nucleus, which is the thing, so they're easier to lose. But the halogens have very full outer shells and are attracting electrons to them. Is that right? Wouldn't that have the same problems? But they have more shells, so why would they get more reactive?
The reactivity decreases going down the group.
Oh! So... Because... Yes, okay, yes. Oh, God, my brain is fried. Yes, so the halogens attract electrons to them. So as you go down the group, each element has more shells of electrons. And so the space they have available to attract an electron to is further away from the positive protons that are the attracting force for any negative electrons they could potentially gain.
All right.
That is the first answer in this whole exam that I feel like I genuinely knew.
And I think you get it.
I do get it.
A teacher investigated the reaction of iron with chlorine using the apparatus in figure 5. The word equation for the reaction is iron plus chlorine goes to iron chloride. The teacher weighed the glass tube and iron before the reaction, the glass tube and iron chloride after the reaction. Calculate the simplest whole number ratio of moles of iron atoms to moles of chlorine atoms. Determine the balanced equation for this reaction.
I can't remember what a mole is. We'll have to skip that one.
Okay. I think we do need to start skipping some anyway, because we've got 16 minutes to finish this bad boy. I'll label it orange. We may come back. We won't. Question 9, Laura. That's the last question. Woo! This question is about citric acid. Citric acid is a solid. A student investigated the temperature change during the reaction between citric acid and sodium hydrogen carbonate solution. This is the method used. Pour 25 centimeters cubed of sodium hydrogen carbonate solution into a polystyrene cup. Measure the temperature of the sodium hydrogen carbonate solution. Add 0.2 grams of citric acid to the polystyrene cup. Stir solution. Measure the temperature of the solution. Repeat steps 3 to 5 until a total of 2 grams of citric acid has been added. The student plotted the results on a graph. It looks like an ice hockey stick pointing to the right. Figure 6 shows an anomalous point when 0.6 grams of citric acid was added. This was caused by the student making an error. The student correctly measured the mass of the citric acid, correctly read the thermometer, correctly plotted the point. Suggest one reason for the anomalous result.
Oh, Christ, I don't know. Anomalous point where...
Do you want to move on?
No.
Do you want to say something?
Desperately. Like, so what's going through my head is the idea that maybe the citric acid is absorbing energy from the solution, and that's why the temperature's dropping in the solution as they add the citric. So adding a smaller amount means it's increased less, whereas when you're adding it at regular amounts, it's increasing at regular intervals.
They measured the mass correctly, though.
What?
They measured the mass correctly.
What do you mean?
They measured the mass correctly. We're trying to work out why that point's anomalous, but they measured the mass correctly.
Well, they've put it on the wrong line then.
No, they plotted the point correctly as well. It says that too.
Why was it? Maybe they took the thermometer out of the solution for a minute? I don't know. Maybe that bit of citric acid was too warm.
What do you mean?
I don't know, Ron. I have no fucking idea what they did wrong. I wasn't there.
Please don't get cross with me. I didn't ask the question.
What did they do wrong? Why is it anonymous?
That's the question.
I don't know. I need my blood back.
What do you want me to write down? Do you want me to write anything down?
Yeah, help me.
You've had so much help.
I haven't had as much help as I had in biology.
I think you have.
I haven't.
It's just one mark. Why don't you
What
seek
is it
help
then?
for
Okay,
a better
so
one?
just help me then. What is happening?
Do you want to know the answer? No, we'll do this in the results app.
No.
Right, let's move on, because you've only got
Stop telling me the time.
11 minutes left. I'll mark it orange and we'll come back, okay? Question 9.2. Explain the shape of the graph in terms of the energy transfers taking place. You should use data from figure 6 in your answer.
Okay, so the solution begins at just shy of 17 degrees. And then the temperature of the solution decreases until there is 1.5 grams of citric acid in the solution. This is because citric acid and hydrogen carbonate solution have an endothermic reaction up to this quantity above the 1.5 gram mass of citric acid, the temperature begins to increase again, suggesting that the citric acid and hydrogen carbonate solution are now emitting energy from their reaction. Stop talking.
9.3.
That felt pretty okay, didn't it?
Till the end. A second student repeated the investigation using a metal container instead of a polystyrene cup. The container and the cup were the same size and shape. Sketch a line of... Oh, you just get those marks, Laura, because we don't do graphies, do we? 9.4, steaming along.
I would expect, Ron, what I would expect would be for the cup to lose energy quicker. Because it's metal, so it's passing the energy out quicker, whereas polystyrene is insulating. But as discussed, I get those points, so don't think too hard about it in case that's wrong.
Almost snatched defeat from the jaws of victory there. Right. The student used a solution of citric acid to determine the concentration of sodium hydroxide by titration. The student made 250 centimeters cubed of a solution of citric acid of concentration 0.05 moles per decimeter cubed. Calculate the mass of citric acid required.
No.
Okay. This is part of the method the student used for titration. Measure 25 centimeters cubed of the sodium hydroxide solution into a conical flask using a pipette. Add a few drops of indicator to the flask. Fill a burette with citric acid solution. Describe how the student would complete the titration.
I don't know what titration is.
Give 2 reasons why a burette is used for citric acid solution.
Because it evaporates at room temperature. So you need it in a closed transport system.
You're just assuming burettes are closed.
Yeah, isn't it like a burette? I don't know. And 2, it is dangerous on your skin. So it's safer than a teaspoon. Oh, and get rid of that safety question. Get rid of that one, Ron. You can do more precise measurements with a burette. I should have looked up what a burette was in the intervening weeks.
So you want to get rid of the teaspoon one?
Yeah.
More precise measurements.
Yeah.
Okay. Done. 9.7, Laura. Last question.
It doesn't look like one I'm going to try on.
No, 13.3 centimeters cubed of 0.05 moles per decimeter cubed citric acid solution was needed to neutralize 25 centimeters cubed of sodium hydroxide solution. The equation for the reaction is thus: calculate the concentration of sodium hydroxide solution in moles per decimeter cubed.
Can't. Don't know what a mole is.
All right, are we done?
No, what have we got to go back to?
Fuck, you actually want to do that?
Yes, Ron.
All right, we've got 6 minutes.
Okay.
So we're going back to, firstly, 7.6.
Okay. This is that fucking car. Okay. The energy needed for a car powered by a hydrogen fuel cell to travel 100 kilometers.
Out of all of them, you can get this one. This one is simple.
It's 58 megajoules. The energy released when 1 mole of hydrogen gas reacts with oxygen is 290 kilojoules. I don't know how to turn 290 kilojoules into 58 megajoules, though, because I don't know what a megajoule is.
Do you know what a kilobyte is?
No.
Do you know the relationship between a kilobyte and a megabyte?
No.
Do you know which one's bigger?
Megabyte.
Okay. Do you know what a gigabyte is?
Bigger.
Yeah. Do you know the difference between like something being nano and micro?
No.
Oh, we've talked about all of this. Have a guess.
Let's call it thousands. 58,000 kilojoules is what I'm going to call that, just for time. So I'm going to say 58,000 divided by 290 equals 200. Feels like a good round number. I'm pleased. What am I supposed to be doing? 200 moles, let's say. Volume of 1 mole. So then I'm going to multiply 24 by 200. 4,800 decimeters cubed.
All right, next one that you skipped was 8.6.
Oh, it's always the 0.6s that I hate. Right.
This one was also about moles.
Yeah.
You really should have learned what a mole was.
Well, I didn't know it was going to come up every question, did I?
We did do it twice. Do you remember the moles redo?
Yeah. Oh, God. Teacher investigate the reaction of iron with chlorine using equation. Word equation is that? Right. So the glass tube is 51.56. So I'm going to do 56.04 minus 51.56 equals 4.48. That's my iron. Then 64.56 minus 51.56. 13 is my iron chloride. Meaning that 13 minus 4.48 is my chloride.
How much is that?
What?
How much is that?
What do you mean?
How much is that? I'm trying to record your answer.
How much is what?
13 minus 4.48.
Oh, 8.52 is my chloride. Hey, baby.
Let go of the steps. Let go of the steps.
I love it when she pretends to want me because she doesn't want to do what he's asking. Makes me feel warm inside.
Yeah. But instead, you're sat up doing this, missing the best years of her life because you're doing GCSEs.
Oh, God. I mean, okay. And then the relative atomic mass of chlorine is 35.5. So that's 71 for chloride. So I'm going to do 71 divided by 8.52.
Where's the 71 come from?
Well, because chlorine is 35.5, so I've times it by 2 to get chloride.
Okay.
Is that not right?
Couldn't possibly say.
Okay, then.
You've got 1 minute.
I don't even really know what I'm trying to get to in this one. Moles of iron atoms, moles of chlorine atoms. Jesus. Okay, so let's just 56 divided by 13. I'm going to say there are, how many numbers do you want?
A ratio. 1 to 1.
13. Shoot. And stop. Chlorine 8.56. No. 35.5 divided by 8.56 equals 4. 4 to 13.
Okay. Let's stop there.
I tried, Ron.
You tried really hard, and I'm impressed by that. You went back to questions which you didn't even bother to do in biology.
I think in biology, I genuinely forgot.
Wah, wah, wah. That's the time. Oh, God, that was
Horrible.
really something.
Have fun editing that, Ron.
Yeah, that's a longie because we fucked up at the beginning
Oh, we
as
can
well.
just cut that off, though, I think.
Oh, no, it's good content.
I don't think it is.
Gotta milk it.
All right, Ron, that was it. That was the last episode of the year.
Bloody hell.
And we'll be kicking off 2025 with the results of that chemistry exam. Although technically we're kicking off with Buoyancy 3, because that makes sense canonically. So for patrons, you're getting a new episode on Friday morning, the third instalment of the novel Ron and I are writing together, set in the fictional Cornish town of Callanpiro, at the bed and breakfast, the Buoyancy.
Like being forced at gunpoint to write prose.
I really like those episodes, and I think they're fun.
Yeah.
We've got some fun stuff planned, though. I've been planning when things are going to get released this year. We've got a Detentron coming up in January, which we haven't done one of those for a while. So we're going to be doing aeroplanes, how and why they work. Then in February, it'll be the first episode of our D&D campaign featuring husband of the podcast and girlfriend of the podcast.
Are we announcing that now?
Sure.
Okay, wow. Because that's coming hand in hand with the new tiers on the Patreon.
Yeah, I don't really know what that is, though, so that's up to you to explain.
Yes. Well, I'm not ready to explain that yet.
Okay, well, we'll explain that next time, unless we forget, in which case it'll be another time. And then we've roped younger sister of the podcast, Meg. She's coming back in March to do another 2 Crimes and a Lie.
All right,
That
here's
got an
the idea.
outstanding reaction.
The idea is...
No, think it through. Don't just start launching things out
No.
into the world that you won't stick to. I will not let you do this. No. Ron, we've got to thank you.
No, I've got the idea.
No, I want it planned and thought out. I don't want you making promises that only last for a week.
But no, but the thing is, it's no extra effort for us.
We'll announce it in the new year.
Okay.
Ron, can you please read the register?
Oh, I don't have it open.
Oh, Ron. It's because I wrote it, because I'm the queen of organisation today.
Episodes. No, that's in... I clicked on live shows by accident. Episodes.
Gosh, it's a climactic end to the year, isn't it? Ron,
1,
scrolling
3,
through
3.
folders. Please edit this out, Ron.
I don't edit intros, outros.
You simply must. What if they a little
Just...
fart?
Do you want to do the music?
Oh yeah. Bum ba-rum ba-rum bum 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 ba-dum da-dum bum 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 ha hoo ha ha hee hoo hoo hoo.
The big Christmas gooch thank you to Justin Thompson. Justin is our official crime committer. Due to the overwhelming and phenomenally positive response to our 2 Crimes and a Lie episode with the younger sister of the podcast, Megget, we now need to make sure that there's a permanent supply of crimes to keep her busy researching. And so Justin is hereby permitted to go back in time and commit wacky historical crimes that she can tell us all about. Good luck, Justin, and we'll be making a 20% commission off all booty. The next 2 Crimes and a Lie will
No,
be
you can
beginning
stop
of
there. That's just notes.
Sorry.
That's just notes. We've already done the bit. Thank you, Justin. Justin not only signed up out the blue, Justin signed up to an annual one.
Just
For the
in
princely sum of,
time.
like, £35. You get a whole year of Patreon stuff. And I believe Justin is still working his way through, so won't even hear this thank you for a little while.
That would be a lovely delayed gratification.
Yeah, that'll be beautiful. Did you notice, Ron, by the way, that younger sister of the podcast, Meg, signed up as a free Patreon member?
No.
I don't even know what that free thing does.
I think you just get the notifications.
Like, just to tempt you.
But you can't. We could release stuff for free if we wanted to, so...
We won't. We release this whole fucking podcast for free.
Yeah.
All right.
We
Well,
could give her the episodes.
Yeah. She wrote them.
I used to have to pay for National Treasures
Yeah, but
Patreon.
you make about as much as 2 of our siblings put together, so...
Yes, I am wealthy.
All right, everyone. Have a very lovely year. Be safe tomorrow night. And thank you for another sparkling year of making Lex Education. Are we entering our 4th year of creating it, Ron?
We did start in the new year, didn't we?
We started recording. Was it 2022 we started?
Yeah.
Yeah, so this 22, 3, 4. This is our 4th year of creation we're about to enter.
Can that be right? Because we're only in year 2 of releasing it.
But we were releasing in 2022, and then 2023, then 2024. Now it'll be 2025.
Wow. Goodbye, everybody.
That's maths.